put like B in terms of A, C,
Yeah,
D?
A, C, and D, and since we already know A, or C and D, then we'd be able to solve for A then.
You could, but I guess it would depend on how complicated the problem is if you wanted to do that. If you ask 20 people, you'll get 15 different ways to do this. So it's one of those things where if you know of a faster way, by all means use it. Exactly. As long as it works. All right. Yep. Okay, so go to our old reliable formula here. So we know that the integral of 1 over x to the third times x plus 2 with respect to x equals the integral of a over x. So that's a is 1/8, so we can just bring that 1/8 times 1 over x plus b over x squared plus b is negative 1/4. We might as well make that minus. Times 1 over x squared plus c over x to the third. So c is 1/2, so plus 1/2 times 1 over x to the third. And d over x plus 2, d is negative 1/8, so minus 1/8 times 1 over x plus 2 with respect to x. Okay, so this one will just end up being the integral of x to the negative 3. And this would just end up being the integral of x to the negative 2. Both of these would be natural logs, so they're pretty quick. Okay, so this will end up being negative 1 over x. Okay, and this will end up being negative 1 over x squared. Okay, so you get 1/8 times the natural log of x minus 1. Oh, actually that comes down and becomes plus negative 1/4. Yep, plus 1/4. I guess you could say 1 over 4x. Now let's make 1 over 4 times 1 over x. Okay, and that becomes minus 1/2 times 1 over x squared minus 1/8 natural log of x plus 2. Okay, now if we wanted to simplify this a little more, well, plus c, of course. Okay, we could have 1/8 combining these two. If you remember your rules for logarithms, and I'll write it here. Natural log of m divided by n is equal to the natural log of m minus the natural log of n. And it works in reverse too. So if you have 1/8, the natural log, oh, that should be absolute value of x. I did that to see if you were paying attention, and you all failed. All right, so you have natural log of x minus natural log of x plus 2 plus, I guess you could say 1 over 4x if you want to, minus 1 over 2x squared. Okay, so we can just combine those two together. So that would be 1/8 natural log x over x plus 2. And if you wanted to factor out 1/2, you could. You don't have to. 1/4 x minus 1 over 2x squared plus c. Yes?
For integrating the x to the negative third, doesn't that turn out to be negative 1 over 2x squared?
Yep, where'd I put? Yep, didn't I put negative 1 over 2x squared?
No, because that's 1/2 times 1 over x squared. Because there was a 1/2 in the original.
Oh, yeah,
Well,
that's right.
well,
Yep, I
well,
did supposed to put that. So what? Wait a minute, let me
right
see.
there.
Negative 1/3. What did I miss out? Nope,
So
no.
the integration of x to the negative third
Mm-hmm.
would turn out to be x to the negative 2 over negative 2.
Yep. So you're right.
Do over
Yep, I
the
missed that one.
new exponent.
Yep. So that should be 1 over 4. Yep.
Yes.
Where is it? Missed that one. 2x squared. And that would be over 4x squared here. And 4x squared there. All right, so any questions on this one? Okay, so that's the technique you would use if you had repeating factors in your denominator. All right, he wants to writing. Oops, leave that. Looks like everyone's almost done. Okay, so now we're going to look at irreducible factors. Okay, so let's say if we let f of x equal some p of x over q of x, let's say where q of x equals some irreducible factor. Uh-oh. Say px plus q to the power of m. Okay. Then the partial fraction decomposition includes, so your p of x over q of x would just equal a1, same way you have with your repeating factors. Px plus q plus a2 or px plus q squared, and it keeps on going. Px plus q to the m power. Okay, so that's if it's linear. So you use the same approach that you would before. But if it's quadratic and it's non-reducible, it's a little bit different. Okay, so what if we let, again, f of x, p of x over q of x, but this time, q of x, should be an is in there somewhere. That's going to bug me if I don't put it there. Irreducible factor. This time it's ax squared plus bx plus c, not squared, to the nth power. Okay, then we would write it as p of x or q of x, which equals a1x plus b, b1, over ax squared plus bx plus c, plus a 2x plus b2 over ax squared plus bx plus c squared, plus, and it keeps on going, an x plus bn over ax squared plus bx plus c to the nth power. So these can really become very large very fast. Okay, so each one of these would be different. So you would have probably realistically ax plus b, cx plus d if you had squared. All right, so let's do the example. Leave that up for a few seconds. All right, so let's say, for example, if we have let's say if we want to find the value of integral, well, actually just make it, yeah, might as well go ahead and do the whole thing. 3x plus 2 over x minus 1 times x squared plus 1. Dx. Alright, so the solution for that one, we start with our denominator. Okay, this one's distinct linear. But this one's an irreducible quadratic. Okay, so that means this is going to equal, for this one, it's just going to be ax plus b over x squared plus 1. And you don't have to use the cx plus d because it's only to the first power. If you had to do the second power, then you have to have plus cx plus d over x squared plus 1 squared. So it would kind of keep building up. So it's when you get to that where it really takes up some space. So, okay. Plus we have our distinct factor, so that's just c over x minus 1. Or if you want to make it a over x minus 1 plus bx plus c, you could do that too. Alright, so the first thing we're going to do here, like denominators. Well, I might as well put the x plus 2 over here instead of rewriting it. Okay, so we're going to get our like denominators. Okay, so we have our x plus 2 over x minus 1 times x squared plus 1 equals, give it a little bit of space, so ax plus b over x squared plus 1. The only thing missing is the x minus 1. So we have x minus 1 over x minus 1 plus c over x minus 1. The only thing missing is the x squared plus 1. So times x squared plus 1 over x squared plus 1. Okay, so as soon as you multiply it across by the denominator, those will all cancel out. So you have x plus 2 equals x minus 1 times ax plus b plus c times x squared plus 1. Uh-oh, don't know why I put 11 there. Okay, and this is where we're going to use our strategic substitution. Okay, so the first one is x equal 1, because that would just get rid of that whole first term, and we can solve for c. Okay, so you have 1 plus 2, which is 3. That disappears. 1 plus 1, or 1 times 1 is 1, plus 1 is 2, so you have 2c. Okay, so if we, uh-oh, why did I put a plus when it's equal? Okay, divide both sides by 2, you have c equals 3 over 2. Okay, so just like before, we don't have any more strategic substitutions we can make, because if you put in -1, it doesn't matter because it would still come out to be 1. If you put in +1, it doesn't matter, so it wouldn't disappear. Okay, so we're going to use the coefficient method again. Method of equating coefficients. Let's clean that up a little. It gives us x plus 2 equals, we can go ahead and FOIL that one out. You have ax squared. Your outer is plus bx.
Can you move it up?
Oh, sure. Your inner is minus ax. And your last is minus b. Plus cx squared plus c. Okay, so if we go ahead and combine our matching exponents, or matching variables and exponents, x plus 2 equals ax squared plus cx squared. Plus bx minus ax plus c. Make sure I got them all.
Minus b.
Yeah, missing the minus b. That's why I always go through and do the little slash out when I'm done, just to make sure I don't miss any. Okay, so if we made this 0x squared plus x plus 2 equals a plus c. Factor out the x squared plus b minus a, if we factor out the x, plus c minus b, which are just two constants. Okay, so we know here that a plus c would have to equal 0. We know that b minus a would have to equal 1 for that to be true. And we know that c minus b would have to equal 2. Okay, so we know that c is already 3 over 2. So this one will be pretty quick to solve. So that's 3 over 2 minus b equals 2. And if we subtract, actually we can go ahead and subtract 3 over 2 from both sides. So negative b equals 2 minus 3 over 2. Make that 4 over 2, so that would be 1/2. So b would equal negative 1/2. Okay, so we have our b. So really we can go ahead and solve for a right here. So if b is negative 1/2, you have negative 1/2 minus a equals 1. Okay, so if we add 1/2 to both sides, that will be negative a equals, add 1/2, that's 3/2. So a equals negative 3/2. Oops, clean that up a little bit. Okay, so we have our a, we have our b, and we have our c. Alright, we'll continue that on the next page. I'll leave that up for a little bit. Alright. Oops. Okay, so that means, go back. To, where is it? Ah, here we go. So this one. So we know the integral from 2 to 3 of x plus 2 over x minus 1 times x squared plus 1 equals the integral from 2 to 3 of ax plus b. So we know our a is equal to, where is it? Ah, negative 3/2. So you have negative 3/2 times x plus b, which is negative 1/2. So we make that minus 1/2. All over x squared plus 1. Plus c over x minus 1, which is c 3/2. Times 1 over x minus 1 with respect to x. Yes.
Could you separate those and factor out a negative 1/2?
Yep, that's exactly what we're going to do. Yep, so we're just going to separate those two. All right, bring that over a little bit. Okay, so we can make that negative 3/2 x, well, times x over x squared plus 1 dx minus the integral from 2 to 3 of negative 1/2. We can just bring that out to the front, so that will make that plus 1 over x squared plus 1 dx plus 3/2 times the integral of 1 over x minus 1 dx. Okay. So the last one, we know that's going to be a natural log. That one's pretty straightforward. And this one, we can actually kind of manipulate that a little bit. So move the negative 3/2. Actually, we can leave it on the inside. Doesn't matter. So you have negative 3/2. And you have x over x squared plus 1. So if you multiply this one by 1/2 and multiply this by 2, you actually get u prime over u. So you just turn this one into a natural log also. Okay, so plus from 2 to 3. Oh, yes.
Wouldn't it also be subtracting the 1/2? Since both are negative in the numerator of the last step.
Where are you looking at?
At the top of the page, both of them are negative in the numerator. Would it be subtracting both?
Yep, I changed that for some reason. Let me see if I made an error anywhere. Where is
You
it?
had a negative and then you were like, but then the negative also makes it.
Oh, I must have just redid the same step
You
over
redid the
again.
same
Yeah.
negative and made it positive.
So I actually did it, then I did it again, which I shouldn't have done again. All right, so you have minus 1/2. And with this one, Oh, actually, we can, yeah, I'll leave it like that and just solve it. X squared plus 1. That one actually becomes a tangent inverse. Plus 3 over 2, integral 1 over x minus 1 dx. Okay, so this one actually becomes negative 3 over 4 natural log of x squared plus 1. And you don't need the absolute value anymore for that one, at least, because it's always going to be positive. Okay, minus 1/2, and that's tangent inverse of x, plus 3 over 2 natural log of x minus 1, which you do need the absolute values for, plus c. Oh, not plus c because it's definite. So we have to actually solve that. Say from 2 to 3. Okay, so you have negative, actually, to make that one, that'll complicate it. I was going to try and combine those two, but no point. Okay, so we have negative 3 over 4. Natural log of 3 squared, which is 9 and 1, so you have natural log of 10. Minus 1/2, tangent inverse of 3. Plus 3 over 2, natural log of 3 minus 1, which is 2. Minus, plugging in 2, so you have negative 3/4, natural log of 2 squared is 4, plus 1 is 5, minus 1/2, tangent inverse of 2, plus 3 over 2 times the natural log of 2 minus 1 is 1. Okay, so this actually just becomes 0 since natural log of 1 is 0. So that leaves us with 3 over 4 plus 3 over 4, so we can actually factor 3 over 4 out of these two. Now I'll use a bracket instead of another set of parentheses. So we have natural log of 5 minus natural log of 10. And plus, we have 1/2 tangent inverse of 2 minus tangent inverse of 3. Plus natural log of 2. All right, so if you wanted to, you can combine these two. You don't have to, but because remember,
If you're getting the 3 halves, the 11 2.
oh, 3/2, thank you. And I look right at it too. Okay, so here, if you wanted to combine those, you could, simply using the rule we used before, natural log of m over n, natural log of m minus natural log of n. Okay, so this becomes natural log of 5 over 10, which is natural log of 1/2, plus 1/2 tangent inverse of 2 minus tangent inverse of 3 plus 3 over 2 natural log of 2. And if you plug that all into your calculator, you will end up with 0.4489. Give or take. Oops. All right, so any questions on that one? All right, so that's how you would solve the irreducible. Yes.